If alien civilizations are truly out there, what will humanity's first contact with them plausibly look like? What kind of civilizations are we most likely to detect? And what signature will ultimately betray their presence to us? I have spent many years pondering this profound question. And today I present to you a radical new theory. One which you will not find in any Hollywood movie or television show. An idea which I call the Eschaton Hypothesis. The secret source history to this idea comes from thinking about the history of observational astronomy. The most prestigious groundbreaking astronomical detections are those that detect entirely new types of astrophysical phenomena. A good example, and subject to my own research, is exoplanets. Even before their discovery, it was widely recognized what a big deal their discovery would be. And multiple teams were trying to pull this feat off. Many looked at the solar system as a kind of template as to what to expect. And thus they built instruments designed to detect Jupiter-like planets on wide distant orbits around their star. But some radical thinkers looked in the most unexpected places. It was Alexander Walshon and his team who started finding the first confirmed exoplanets in 1990. But these were bizarre worlds. Planets orbiting pulsars. A few years later, the first exoplanets around normal stars were found. But again, they shocked the scientific community with the discovery of so-called hot Jupiters. You see, for decades, it was assumed that gas giants like Jupiter would form in the outer regions of solar systems, where it was cool enough for ices to remain stable. But in the late 90s, astronomers kept finding Jupiterized planets 10 times closer to their star than Mercury's orbit around the Sun. Planets with temperatures of thousands of Kelvin. Looking back, with the benefit of hindsight, we now understand that both hot Jupiters and pulsar planets are in fact very unusual rare types of planets. For example, although most stars indeed have planets of one kind or another, less than 1% of them have hot Jupiter-type planets. Now, you might be wondering, if they are so rare, then how come they dominated this early phase of exoplanet detection back in the 90s? Well, the reason is simple. Can you guess it? It's because of detection bias. The reason why we found so many of them is just because they are so damn obvious and loud. You can hardly miss them, in spite of their intrinsic rarity. Perhaps the most poignant example of detection bias in astronomy is just to look up at the night sky. On a clear night, you can see a couple thousand stars above you. And remarkably, about a third of those are giant stars. Essentially dying stars. The Sun too will one day enter this stage. In roughly 5 billion years from now. Ballooning so large it will likely engulf the Earth. But this is a transitory phase, lasting for less than 10% of its total lifetime. Indeed, only about 1% of all stars in the universe are in this giant phase. And yet, despite representing just 1% of the population, they make up about a third of the stars that you can see with the naked eye when you look up at the sky. And of course, the reason for that is again detection bias. Or technically in astronomy, we call it Mommquist bias. Stars become so brilliant as giants that we can see them from far, far further away. For example, Dan in the constellation Cygnus is easily visible by eye despite being roughly 2,000 light-years away. But the nearest star Proxima Centauri just 4 light-years away isn't visible by eye at all. And to cap this argument off, my favorite example of a detection bias would have to be supernovae. The most common type of supernova is a core collapse event. Very massive stars, those greater than 8 times the Sun's mass, have different fates to most stars. A much more violent destiny. Stars are in essence a balancing act of outward radiation pressure and inward gravitational pull. When the fuel starts to run dry, gravity wins out and the star implodes. The outer layers collapse inwards and bounce off the inner dense core, leading to a spectacular supernova explosion. Now, these events are so energetic that for a few days, this one single star can outshine the other stars in its galaxy combined. But like hot Jupiters, these are very rare events though. A Milky Way-sized galaxy gets just one supernova every half-century or so. But despite their staggering rarity, astronomers routinely detect thousands of these things every year. Why? Because they are so damn bright that we can see them from essentially the other side of the universe. So the history of astronomy teaches us that often the easiest examples of astronomical phenomena to detect are in fact highly atypical. Pulsar planets, hot Jupiters, giant stars, and supernovae are all freaks. Extreme examples of their broader class. They are the loud, obnoxious twits at the cocktail party that suck up all the oxygen. Most people don't act that way. But you can bet the rare few who do get noticed by everyone. So, by extension, we should expect the first detection of an alien civilization to be someone who was being unusually loud. Their behavior will probably be quite atypical. But their enormous volume makes them the most likely candidate for first discovery. As the history of astronomy has taught us time and time again. Now, the idea sounds simple. But there is a lot to unpack here. Recall our analogy of a supernova. But that raises the question. What is the civilization equivalent of a supernova? Well, consider that a supernova is really just a phase of disequilibrium. For eons, the star was perfectly stable and quite unremarkable. Gravity and radiation pressure in harmony with one another. The whole reason why this star became so detectable was because of this terminal phase of disequilibrium. So we might imagine that a civilization in disequilibrium with its environment would represent one of the easier types of signals for us to detect. This instability is really any phase where a civilization's energy throughput, environmental forcing, or technological interventions depart sharply from long-term equilibrium, generating disproportionate waste heat, radiative leakage, surface modification, or high-energy transients. As an example, one proposed method that an alien could potentially detect us is anthropogenic climate change. Unnaturally rapid changes in appliance temperature, weather, and atmospheric chemistry. Which is obviously not sustainable. Perhaps the most extreme dicular room we can think of is nuclear war. Detonate all the nukes on Earth and we would light up like a Christmas tree for the whole galaxy to see. Indeed. Astronomer James Elliott explicitly suggested doing this in space as a way of saying hello. And also getting rid of all of the nukes back in 1971. Such an act maximizes our volume, our detectability, albeit only for a brief period. This is perhaps the closest analogy of a supernova that I think we are capable of. This is all particularly potent because detectability scales with luminosity to roughly the 3/2 power because the observable volume grows as the radius cubed. But most critically, what this really means is that a civilization that is 100 times louder becomes roughly 1,000 times more detectable. And this causes these brief supernovae phases to be vastly overrepresented in our detections. The exact method of disequilibrium isn't important. What really matters is the principle. The greater the imbalance, the louder they become. And this idea gels neatly with a previously published idea in astronomy known as the sustainability solution. To see this, consider the thermal image of a housing complex. All those red areas are waste heat inefficiencies. So developers tried to improve the designs to minimize such wastage. And of course, the ultimate goal will be a building that was completely indistinguishable from its environment. And so, the more sustainable we become, the less detectable we are to other alien species. As a twist on Arthur C. Clarke's famous words, science fiction author Carl Schroeder once wrote, "Any sufficiently advanced civilization is indistinguishable from nature." So advanced, mature alien civilizations could be out there. But we would never know about them because they become so sustainable that there's no signature left us to grab onto anymore. The Eschaton Hypothesis leans into this idea and suggests that the most detectable alien civilizations will be the unstable ones. The etymology comes from the Greek eschatos, which translates as the last. The end of all things. Because baked into this is the recognition that instability is inherently unsustainable. One way or the other, this signal, and plausibly the entire civilization, will soon end. Like a supernova. This tumultuous period simply cannot last. The open question with this hypothesis, and one which I gladly concede, is whether these periods of disequilibrium are sufficiently common, loud and prolonged to make them more detectable than the other population of quiet and presumably more numerous quasi-sustainable civilizations out there. Broadly speaking, their detection probability will be a product of those three factors. The fraction of civilizations which are loud, just how detectable they become during that period, and how long this phase actually lasts for. That combination competes with the detectability of quiet civilizations. The Eschaton hypothesis thus suggests that the former will beat out the latter. And to be clear, I am not claiming that this is definitively true. Merely that we should take this idea seriously. Especially given the context of historical astronomical detections that we have seen in this field. There is an undeniable tragedy to this notion. Hollywood has preconditioned us to expect one of two types of alien contact. Either a hostile invasion force, or a benevolent species bestowing wisdom to humanity. But the Eschaton hypothesis is neither. Here, first contact is with a civilization in its death throes. One violently flailing before the end. As an extension to this idea, such a species may even recognize his imminent demise, and decide to consciously send out messages into the void as a kind of last-ditch resort. The late Stephen Hawking often warned against sending messages into space for fear of destruction. A concept foundational to the dark forest theory in Lucia Shin's three-body problem. But in this case, any fears of external threat dissolve when facing internal annihilation. There is nothing to lose and everything to gain. So whereas thus far in this video, I have presented the Eschaton hypothesis as a kind of generic disequilibrium signature. In this modification, it takes the form of a deliberate transmission. Perhaps a radio signal, for instance. Who knows? Perhaps the infamous WOW signal was indeed such a last cry for help. But it has to be said that the picture I have painted for you fully undermines the classic Hollywood portrayal that we have become all so used to. In this contact scenario, we are not the vulnerable party. But rather, we are the ones who serenely bear witness to a train wreck of a civilization. One who is desperately screaming out into the night. In the same way that we can gaze through our telescopes at older sun-like stars turning into giants. A preview of our own solar system's fate. These civilizations could be a premonition of what lies ahead for humanity. I personally have 3 solutions right now in my head for the Fermi Paradox. And the Eschaton Hypothesis is one of those. I do not know if I would call it my favorite. But I do believe it is a plausible solution. And the ramifications are important because it would actually influence our search strategy. If true, we should search continuously broad and deep for short transient events as generically as possible. That is a tall order. But it exemplifies the direction of many modern astronomical surveys like the Rubin telescope that aims to capture a video of the sky in multiple wavelength bands every night. Perhaps this is our best bet. Just to keep our eyes peeled for the anomalies. The weirdos. The loud shouts in the night. Indeed. A recipe that astronomers have followed for centuries with great success. If you'd like to see more content like this, make sure to subscribe to Deep Space Feed.